talk to this bright and energetic group of people. So today I'm going to talk about string vacua. I started thinking about string vacua a number of years back. Giddings, Kocherou, and Polchinski had recently written a marvelous paper on type 2b flux vacua, and there was a lot of discussion about the landscape and whether you could get anything or what you could get, and all the different kinds of constructions. And like most people, I started out by trying to understand four-dimensional vacua and have spent a while trying to understand intersecting brane models, flux vacua into A to B, non-geometric vacua, and things like this. And I generally am motivated by trying to get some global picture of what's going on. And I felt a bit frustrated after a while because I realized that we really still have a very poor sense of what is actually going on in four dimensions. So for the last couple of years, I've been kind of going back to higher dimensions, trying to understand a little bit better what we really know about string vacuum constructions in higher dimensions, and realizing, among other things, that there are a lot of questions which we still don't know the answer to in higher dimensions, where the questions are much simpler than they are in four dimensions. So this seems like a very useful set of things to go through in a pedagogical fashion at a school like this, because although, of course, we all want to understand the physics of four dimensions and how string theory might give us some predictions for what we see at the LHC, there's a big stretch between the Planck scale, where we have supersymmetry and strings in 10 dimensions or 11 dimensions, and what's going on in four dimensions. And to get there, we really, I think, need to have a clear understanding of what the rules of the game are, and the best place to understand those rules is by starting in higher dimensions and working down. So the title of these lectures is The Scope of the Landscape, Supergravity, and String Vacua in 10D, 8D, 6D, and 4D. And those of you paying attention will notice that I stuck in an 8D, which was not originally in the title. Originally, I felt I only had things to say about 10D, 6D, and 8D, but I realized putting these lectures together that 8D is a very important dimension, which in some ways is more similar to four dimensions than 6 or 10. And there's a nice story there which helps to introduce some of the ideas which we need to understand lower dimensions. So I'm going to start in 10 dimensions and move down. Again, a lot of the work in string vacuum constructions has been focused on trying to find the phenomenologically correct vacuum. And this work is extremely valuable. It helps not only to give us a good understanding of what mechanisms you might need in string theory to realize the physics we see in nature, but it also drives some of the research at the more theoretical level in understanding the mechanisms of string vacuum constructions. You know, there's a lot of interesting work right now going on F-theory phenomenology, which, although different people have different opinions about whether it's really going to nail down precisely the right model, it's driving the development of the technology in a direction which is very fruitful for the field as a whole, because there are lots of things we don't understand. So today, basically, this week, I'm going to start in high dimensions in 10, move down, and at each succeeding lower dimension, the problem will become a little harder, and we'll have to develop a little more sophisticated tools. And the idea will be to try to give you a global picture of what we do and do not understand about string vacua in these dimensions as we go down. Just a comment, you'll notice, obviously, I'm intending to use slides for at least some of these lectures. I may switch to the blackboard at the end, depending on how my preparation goes. I've found, actually, that presenting even very complicated material in a pedagogical fashion can actually work very well with slides, and in fact, I prefer it on one condition. And that condition is that we avoid the big downfall of people using slides, which is there's a tendency on the part of the lecturer to whip through lots of material very quickly, and nobody has any idea what's going on. And you have to play your role in keeping me from doing that. The best way for that not to happen is to have an active dialogue. I view the value of using slides instead of writing at the blackboard is that I can go at the same pace, and instead of having me spend lots of time writing down equations, even if it's a big equation and we only need a piece of it, I can just put it up on the board. We can spend that time actually discussing it. So I really want to ask you to stop me if you have questions. Stop me if something wasn't clear on the previous transparency and it just slowly came through that, wow, I didn't really quite get that. Can you go back? I'm happy to stop, go back. I'd like to spend the time in discussion and pace things slowly. That's part of why I'm using the slides. I'm not using the slides to get through a lot of material. I'm using it to give us more opportunity for discussion of things so I can go back. We can talk about things like that. So your job is definitely to ask questions whenever they occur to you. I'm sure there are lots of things we all have to learn from one another. So let me just start out with some general words. So quantum field theory is obviously this great, powerful framework which we can use to describe the standard model of particle physics and all kinds of extensions to it, which we may see at the LHC. But there's lots of freedom in quantum field theory. You can write down a wide variety of quantum field theories. There are a few constraints from anomalies, but for the most part, you have a lot of freedom in terms of your gauge group, in terms of your matter content, your couplings, etc. And our hope as theoretical physicists is that we can find a deeper understanding of some of the structure that we see in nature. And quantum field theory doesn't seem to have within it, at least as we understand it so far, pieces which will give us strong constraints beyond those we already understand. So we want to ask, if we include gravity, are there further constraints on the set of physics, on the kinds of physics you might see at low energy? So the question which at some level will be motivating everything I'm going to talk about this week is, if we include gravity and insist on UV consistency. Uh-oh, my battery's dying. You have a laser pointer? Anybody? My battery has just died. Okay, I will get new batteries for next time. If anybody has 2 AA batteries, that would be helpful too. Maybe there's a stick somewhere. There's a short stick. Okay. Imagine the lightsaber. So the question is, does gravity and consistency at the ultraviolet constrain the physics we see at lower energies? And to address this, I'm going to take 2 points of view. The first one is to try to understand what constraints gravity and quantum gravity impose on the space of possible field theories which we can couple to gravity. So I'm going to call G the set of apparently consistent gravity theories. Oh, sweet. Thanks. Oh, you know what? I might have AAAs. Sorry, I didn't turn it all the way. It's AAA. Anybody have AAAs? Sorry. So we'll call the space G the set of apparently consistent gravity theories. And there are various things which we may be able to use to rule out theories which are classically okay, but which may not have good UV completions. So that's the one piece that we'll be looking at. Oh, awesome. Thank you so much. Hopefully this will solve my problems. Thanks. So the second thing that we'll be looking at, of course, great, thank you so much. The second thing that we'll be looking at is the set of known string vacua, which I will call V. And again, G and V are both at this point dependent on our current state of knowledge. These are not mathematically well defined. These are just, G is the things we are not smart enough to rule out, and V is the things that we are clever enough to find string constructions for. We don't know what string theory is. We don't have a complete set of rules for constructing string vacua. So this set is almost certainly larger than what we can do right now. And there are almost certainly constraints we don't know about. So G is almost certainly smaller than we know. So a number of years back, Vafa coined the term swampland for this murky space of things which are in G but not in V. And so what we'll be talking about in this week basically is, in these various dimensions, what is the space of string vacua, what is the space of things that we can't rule out, and how big is the gap between them, the swampland. The swampland, of course, is monotonically decreasing in scope over time, the apparent swampland, unless somebody makes a mistake, right? Somebody says this is a string vacuum, and somebody later shows it's inconsistent, then the swampland gets bigger again. But right now, we have imperfect knowledge about these things in lower dimensions. As I'll discuss today, there are some cases where we think perfect knowledge in high dimensions. Yes, question?
Can you say a little bit more what you mean by gravity theory?
What I mean is, there are various field theories that you can write down in various dimensions. And I mean just very naively, it's an apparently consistent theory if you can put it in a curved space-time background, perhaps with supersymmetry, and you don't know how to rule that out as an acceptable theory. So there are various ways you might rule it out. One of the primary ones being anomaly cancellation. Other ones might have to do with instabilities. things like that. There are various things you might use to rule out a theory and say, this is clearly a sick theory. Right now, other than string theory, we don't have any good way of saying whether a theory is UV complete as a theory of gravity. So we can't rule things in, but we can rule things out. So G is the complement of the set of things which are obviously sick, or provably sick. And V is the set of things we can get through string theory. Let me just pause. Yes, question?
I mean, presumably there could be things which are apparently inconsistent, but are actually consistent when you include string effects.
It is possible, however, the rules we're going to use for determining inconsistency, we would like to use rules which are so stringent that it is hard to imagine ways of fixing things up. It is quite possible that at some point somebody might take a theory that we thought was sick and find a way of fixing it up. That's certainly possible.
I mean, like an orderfold. I mean, that doesn't mean string effects and something else.
Right, but I would say a singularity is not enough to signal that a theory is sick. If you see a singularity, it usually means that there's something happening in the UV that you don't understand, which may or may not fix it up. One of the beauties of string theory is it can fix up a lot of low energy problems. Anomalies, for instance, are a rather different kind of thing because they break a gauge invariance at the quantum level in a way which is manifest in the low energy theory. So there are certain low energy sicknesses which characterize certain bad theories, which it's very hard to see how to fix up. And those have to do with things which clearly either represent instabilities or breakdowns of fundamental symmetries of the theories. So I'm going to try to be pretty minimal about what I use to rule things out. But obviously, somebody can make a mistake and try to rule things out, and they haven't, as Joe said, there are always conditions being put in, and you don't always question all of your own assumptions, and sometimes one of those assumptions was critical, and somebody can circumvent what you said, as Joe said, by a counterexample. Good question. Other questions? Okay. So I'm going to today, this week, completely focus on supersymmetric theories. Supersymmetry breaking is an important and fascinating topic. We don't have supersymmetry in the world. But there are lots of reasons why we expect that nature, at least at some high energy scale, may have supersymmetry. There are reasons motivated from phenomenology, and I'm sure people are familiar with the coupling constant unification, that if you include supersymmetry at a high energy scale, the three coupling constants unify at this nice point. Dark matter, of course, we know from WMAP and other experiments that there seems to be some additional matter in the universe whose nature we do not know. And supersymmetry gives a natural explanation for dark matter. It's an extra symmetry, and there will be a lightest supersymmetric particle, a lightest particle which cannot decay without violating supersymmetry, and that would be a candidate for the dark matter, which we believe exists, might even be seen at the LHC. And there's the famous hierarchy problem. Why is the electroweak symmetry breaking scale so low compared to the Planck scale? Which is related to the question of how we deal with the loops in the scalar field. If there's a Higgs field, then in principle the loops should give a very large contribution to the mass of the Higgs. Why does that scale associated with the Higgs and electroweak symmetry breaking come in so low? Supersymmetry can help solve that problem. There are also some string theory motivations for looking at theories with supersymmetry. One of them is that, of course, string theory needs supersymmetry, at least as we understand it in most frameworks, at the Planck scale to solve the problem of, for instance, the bosonic tachyon. There are, of course, scenarios in which you can make sense of those theories, but most of what we understand about string theory is predicated on the existence of supersymmetry at the Planck scale. And, of course, supersymmetry makes life simpler, and that's one of the reasons why we'll be incorporating it, because we can actually figure things out if we assume supersymmetry. So the worldview I will be taking this week is that I will basically split up the physics of nature into two parts. There's the physics above some intermediate energy scale, lambda, and above that scale we have quantum gravity giving us a supersymmetric quantum field theory coupled to gravity, or a supergravity theory. And then at some scale below that scale, supersymmetry will be broken and give us the observed physics that we see in nature. Now, if this is true, then the physics below that energy scale should be something we can understand using the rules of ordinary quantum field theory. It may be that we want to use string theory to understand the mechanisms or the reason why a particular field theory mechanism would break supersymmetry, but the dynamics of what's going on here should be something we can understand in field theory. The physics up here is something that we need quantum gravity to understand, and that's what we will be focusing on. It's possible this is wrong. It's possible we will not discover we will not discover supersymmetry at the LHC. Supersymmetry is broken at the Planck scale. And all I can say is good luck to the generations of physicists who will be trying to attack that problem, because it will make life very difficult if supersymmetry doesn't help stabilize and simplify the theory of nature above some attainable energy scale. It's hard to do string theory where you break supersymmetry at the Planck scale. So let me pause. This is sort of all the motivational stuff at the beginning here, so let me pause for other questions. Yes?
You said string theory needs supersymmetry. So is there any theorem that says it is impossible to construct consistent string theory without supersymmetry?
No, and in fact, there are consistent string theories without supersymmetry. We believe. People have argued that, the traditional story of string theory is people tried to quantize the bosonic string, and that works in 26 dimensions, but there's a tachyon. There's a closed string tachyon. And that makes the theory unstable. Now, it's possible that you can rescue that by having that tachyon roll down to some other point, which is actually a more symmetric string theory. We know that the open string tachyon was an artifact of our lack of understanding. It was actually a tachyon on an unstable d-brane, and the open string tachyon can go away and leave you in a spacetime without the d-brane. It's possible that something like that happens in the closed string theory, and Seebach and others have found some evidence that maybe something like that is true. We don't yet understand that very well. The things we understand best about string theory involve supersymmetry. But there's no no-go theorem. I don't know. Other questions? Yes, please.
Well, on that, isn't there a non-supersymmetric string theory? I think it's constructed in Joe's book.
Yes. No, there are other non-supersymmetric string theories. There are tachyon-free, non-supersymmetric string theories. It's hard to get large sets of things which look anything like phenomenology out of them. I don't know, maybe, Joe, you would disagree with that statement.
Well, that particular theory in one loop is not stable.
Oh, it's not stable.
It has a tachyon, but there's one loop potential. So it's going to run off in some direction, and you have the usual stabilization.
I mean, people have made arguments that various different non-supersymmetric theories make sense, and I haven't analyzed those carefully enough that I can say definitively that all of those have some problem. But I don't know of any which are compelling and which make us think, oh, there's a whole landscape of non-supersymmetric string theory vacua we should be looking at. Okay. So the plan of these lectures is, basically, I'm going to describe the set of supergravity theories with various kinds of gauge groups, matter content, etc., going down in dimensions, and also the string theories, as I said, these spaces G and V, starting in dimension 10 and going down. And as I mentioned, life gets simple in high dimensions. In 10 dimensions, we basically just have gravity. There's a couple of gauge groups you can throw in, but it's basically just a gravity theory, and life is pretty simple. And today's lecture will basically focus on going over the story in 10 dimensions, where there's a pretty clear picture of what we understand about the set of gravity theories and what we understand about the set of string theories. Even in 10 dimensions, there's an interesting question, which there are some things that we don't fully understand. In the next part of the lectures, I'll talk about 8-dimensional theories, where now we have gauge multiplets, and therefore a wide range of possible gauge groups, and that adds some structure. And so when we get to so in the 10 dimensions, the things we'll talk about will be anomaly constraints, and we'll talk a bit about strings and branes in our discussion of how we can realize some of these supergravity theories in 10 dimensions from string theory. In 8 dimensions, we'll introduce the heterotic and F-theory types of compactifications of string theory. The theories will get a little richer and have more structure. We have more vacuum constructions. And as we go down in dimension, a global picture of what we can confidently say about the supersymmetric string landscape becomes harder and harder to attain. As we get down to 6 dimensions, we now have matter multiplets. So we have all kinds of things in different representations of the gauge group. Again, things get more complicated. Down in 4 dimensions, things are very complicated, and we have very little sense of how to give a global picture of things. But I'll try to talk about each of these things in turn. Again, there's 4 parts of the lectures. There are 5 lectures, so probably they will run over a little bit, and we'll see how far we get by the end of the week. I should add that much of what I'm going to talk about in the first part and half of the second part is a set of things which have been understood for many years, and in fact, almost all of it is in Joe's book. So But I'm going to try to bring these things together, a bunch of ideas which we need to discuss vacua in lower dimensions. I'll try to put these together in a coherent way, sort of picking a bunch of different pieces that we need to draw this global picture. But of course, since Joe wrote the book and is the expert, you feel free, Joe, to chime in. And I mean, the interest here is in getting the fullest understanding to the students. So please, there's lots of things I'm ignorant about. I'm always happy to have my ignorance pointed out. Well, not always, but at the end of the day, I'm always happy to have my ignorance pointed out, even if at the time it's a little painful. But there are lots of things. Thank you very much. Actually, somebody gave me 2 batteries. Thanks so much, KT. Okay, so that's the plan. We're going to go from 10 down to 4. And in each dimension, we're going to say what we can about the space of theories that we can't rule out and the set of things that we can actually get in string theory. And we'll compare those and see how they fit together. Question?
This progression from gravity to gauge groups to Mata-Yukawas, is this only in the case where you're doing F-theory constructions, or to what extent can you get that from?
No, that really comes from the structure of the supersymmetry. I mean, basically, as we'll see, in 10 dimensions, there's just one supersymmetry multiplet, and it has the graviton and everything else in it. In 8 dimensions, you have gauge groups, and that's because the reason I say that is because there's a gauge multiplet. I think it might have even been Tom who first said something about this sort of sequence of things, but it's a very nice way of characterizing the set of things you get as you go down in dimensions. It's manifested in F-theory, but that's just because F-theory is realizing the set of things that you can get, some subset of the set of things you can get in supergravity. Really, the structure, I would say, comes from the supergravity theory in the sense that, here in 8D, we've got a gauge multiplet, but not a matter multiplet. In 6 dimensions, we have a matter multiplet. So it really is inherent in the structure of the supergravity theory. And we'll see that as we go down. Good question. Other questions? Yeah, we'll see how F-theory realizes that and how other models also, other string models, realize that increased structure as we go down. So that's partly why I want to start high and go down, because rather than throwing everything at you all at once, we can just see piece by piece how the components of a string compactification work. We'll start with the gauge group, then we'll have matter, and then we'll talk about the big mess in 4 dimensions. Okay, other questions? Okay, so let's talk a little bit about supersymmetry, so we know just at a very general level what we're talking about. I'm sure everybody has heard something about supersymmetry, but let me just write down a few equations or put up a few equations just to put us all on the same page. Supersymmetry is, of course, a symmetry which relates bosons to fermions. And the important thing about the supersymmetry from the point of view we're going to discuss it today has to do with the fact that the supersymmetry algebra is really an extension of the relativistic Poincare algebra. The anti-commutator of 2 SUSY generators, a Q alpha and a Q beta bar, is proportional to a momentum, P mu, associated with translation in space-time, with a gamma matrix connecting all the right representations of the Lorentz group. Typically, supersymmetry will act on a bosonic field like a scalar field. Its transformation under supersymmetry will be some supersymmetry parameter epsilon times a fermionic field. And the translation of the fermion will be something like, in the case of just a simple scalar fermion, delta psi is going to be proportional to d mu phi with a gamma matrix, again, to saturate all the vector and spinor indices. Often supersymmetry is written with auxiliary fields to make life a little clearer. I'm not going to talk too much about explicit supersymmetry transformations, but underlying the multiplets that I'll be talking about, there's always some supersymmetry algebra like this, and you can always take the Q's and turn them into, you can take the gammas and turn them into a Clifford algebra, and this representation of supersymmetry can be understood in terms of the representations of the Clifford algebra. And there's a nice appendix in Joe's book which goes over all this in different dimensions in a very nice way. Yes?
I just wanted to make a quick comment.
Yes.
It's not quite accurate because you can write down theories which are not Poincare invariant, but which have this symmetry, supersymmetry.
Good. Okay, that is a good point. There are theories which are not Poincare invariant which have this symmetry. All the ones that I'm going to be talking about do have Poincare invariance. So for the theories we're talking about, this algebra is always going to be essentially correct, but it is not to say that there are not other supersymmetric theories. I don't know as much about those other theories, but I'm sure that there's a lot of interesting things one could say about that too. Good. Thank you for that comment. Other comments?
Can you get an example of that? What theories?
I'm going to ask him to give an example of that.
Well, you can. So for instance, in 2 + 1 dimensions, you can write down terms that involve the spatial Laplacian of a superfield, and it will break. It breaks. So you can write down, for instance, a gauge theory, and it breaks. It doesn't have contrary invariance, but it does have this supersymmetry algebra.
Yeah. Maybe you can give a little one of the student talks on that, actually, because I think people might find that interesting. Yes, Tom.
Yeah, there's another very general result, which is if you take a Poincare invariant theory and do what's called discrete light-gun quantization, which is you compactify a light-like direction but only keep a finite number of momentum modes in that direction. You break Poincare invariance, but you leave over the whole supersymmetry algebra.
Good.
The Q's and the P's are still generators.
Yes, this is like a non-relativistic version of...
Well, it looks like a non-relativistic version, though it has peculiar... The mass is a very peculiar...
Yeah, well, for instance, as you well know, in matrix theory, we see something precisely like this. Yeah, so Tom's point is an excellent one, that there are non-relativistic pictures of relativistic theories where you have series like this. So I don't mean to say that this is all you can get by SUSY. It's what we're going to be talking about in this series of lectures, is where we have theories with Poincare symmetry extended by supersymmetry. In some cases, there are multiple supersymmetries, in which case we put an extra index on there, A, running from 1 to script n. That indicates the number of supersymmetries, and it means that we have a bunch of different Qs whose anti-commutators in general will have a delta AB. One other thing we can do is we can extend the supersymmetry algebra by central charges, ZABs, things which commute with everything in the Q and the Poincare algebra. This is not actually the most general form of central charge. There are other central charges which carry Lorentz indices. There could be a mu nu lambda or something here corresponding to an extended object rather than point-like things. This would then be saturated with some gamma matrix. I won't be talking too explicitly about these. I just want to kind of give you a little sense of some of what happens with supersymmetry. The thing that's most important for what we're going to be discussing today is that if you have gravity with diffeomorphism invariance, and that goes over to the local Poincare invariance, and we have supersymmetry, then putting those things together, we get local supersymmetry, and therefore we have a supersymmetric theory of gravity. In other words, if these guys anti-commute to be a p mu, which is a translation, and we have a general relativistically invariant theory, that means that we're invariant under general diffeomorphisms generated by general local transformations associated with vector fields. We can talk about that in terms of the extension to supersymmetry. That gives us a theory of supergravity. So what we're going to be focusing on is supersymmetric theories which have local Poincare invariance, supersymmetry, and therefore which are supersymmetric theories of gravity. That's the ballpark in which we will be playing for the week, is supersymmetric theories of gravity. And I think Joe said that there were, 3 things in ADS-CFT that went beyond what we've seen in nature that were interesting. And I think we're going to be basically focusing on precisely those 3 things. Supersymmetry, extra dimensions, and string theory, I think, were your 3 items, right? For a large part, that's the focus of today's lecture. So, okay, any questions on supersymmetry? Okay, so let's now go up to the highest possible dimension in which we can have a supersymmetric theory of gravity. And that is actually 11 dimensions. If we go up above 11 dimensions, then when you write down your representation of the gamma matrices, that gives you a Clifford algebra, it is going to have a representation with at least 64 states in it. It's a 64-dimensional or higher representation. And even if you start with a scalar and you look at what the various spins of the states that you produce are, you are forced to include states of spin greater than 2, massless states of spin greater than 2. Now, as far as we know, no one has ever been able to write down an interesting interacting theory of massless fields of spin greater than 2. There's a bunch of interesting work recently on infinite hierarchies of higher spin gauge theories in ADS space, which is quite interesting. I'm not going to talk about that here. If we just focus on theories which don't have massless particles of spin greater than 2, then we're basically stuck in 11 dimensions or lower. So those are the kinds of theories I'm going to talk about. Yes?
Is there any compelling sort of proof of that in flat space?
I think that you can use Coleman-Mandula to say something about that, but I don't know how to prove it rigorously. I don't know.
For spin 3 or higher, Coleman-Mandula certainly proves it. Because there are tensor charges that have to be conserved if you have a spin 3 particle, and then Coleman-Mandula shows you the S matrix has to be met.
Right. So how does that break down in ADS?
Well, there's not an S matrix.
Also, the ADS scale sort of gives you a loophole here. It acts like a mass shift.
Yeah, that's fair. That's fair. Yeah, so I think Coleman-Mandula does do it. I should probably be 100% convinced by the argument, but.
You just say Coleman-Mandula plus the fact that massless particles always have gauge invariance.
Yes. Well, basically, anytime you have the massless particle with spin, it's going to have some gauge invariance to get rid of the extra helicity. So it.
And you run out of gauge invariance if at some point you've got to gauge invariance beyond that.
Yeah. Forgive me. There is a standard argument. I'm trying to be a little conservative here because everybody keeps saying, where's the hole in that argument? And I'm afraid that if I come down and say, yes, it's absolutely ruled out by Coleman-Mandula, then somebody's going to find a hole. So it seems that it's ruled out.
I think it's some sort of bizarre pathological string theory where all the states go to, all the massive states go down to.
Yeah, I mean, it is interesting that string theory has infinite hierarchies of massive fields. There are certainly bizarre things that one could consider and imagine violating that, but let's just stick with that for now and put it on a list of things labeled assumptions. And here we think there's a strong. I mean, as Tom says, there should be there's a pretty convincing argument based on Coleman-Mandula, but whether there are holes in that, I won't venture to say. But I'll just take for granted, moving from here, that we're not going to include massless particles of spin higher than 2 in our multiplets. So with that assumption, the maximum dimension for supergravity is 11. And we have a very nice, simple situation where we have one supersymmetry with 32 supercharges, Q alpha. And we can write down the representation of that superalgebra. And we can write down the particle states in the massless multiplet. And we find that the states consist of a graviton, a spin 2 field. And the states in the graviton are characterized by the little group, which is SO9. So it's symmetric, so it's 9 times 10 divided by 2. Take out the traces. 44 degrees of freedom. We have an antisymmetric 3 form, which is just like a gauge field A mu, except it's got 3 indices, mu, nu, lambda, and it's antisymmetric in the 3 of them. And that lives in a representation of SO110, which can be who's in the massless situation, which can be characterized by an antisymmetric representation of SO9. So we have 9 times 8 times 7 over 6, which should be 84. And you add those up, and you get 128, which is the number of degrees of freedom in the graviton, which has a vector and a spinor index. And obviously not all those degrees of freedom. That's a.
Surely mean gravitino.
I do mean the gravitino. Sorry. I think I just copied that line. Sorry. Absolutely. The first of many things which have to be corrected. Good. Thank you, Tom. Okay. Good. Gravitino. So they're the same number of bosonic and fermionic degrees of freedom, and there is a known action which combines those things in a nice way, which is invariant under supersymmetry and is essentially the unique supersymmetric action. And it's got all the main pieces that we're going to be seeing over and over again. So let's just look at it. The action has here essentially 3 parts. It's got the curvature, the Einstein-Hilbert action, with the root g out front as usual. This is a 3 form. C is a 3 form, so its exterior derivative is a 4 form. Therefore has a field strength, F. And just like Yang-Mills theory, there's an F squared contribution to the action. So we have gravity, we have the 3 form potential, 4 form field strength. And then there's a Chern-Simons term, which is a maximum dimension exterior form formed from the wedges of the C and its exterior derivatives, which this kind of term will come into play in lots of gravity theories. So this is the unique supersymmetric theory of gravity, which can be realized in 10 dimensions. sorry, in 11, yeah, sorry, I'm not speaking clear. This is the unique theory which can be realized in 11 dimensions, and therefore in this desired global picture, we have a G in 11 dimensions, which just has one theory in it, which I'll call M11, because, as we will discuss a little bit more later, this can be realized through the branch of string theory known as M theory. So I would say that in 11 dimensions, saying that we have a supersymmetric theory of gravity is a very constraining, it constrains our set of possible theories very strongly. Already, we're so constrained that when we look at this set G, it only has one element in it, and we're done. And what we're going to do is now go down in dimension and see how the set G gets bigger and bigger, and we want to learn what we can say about it and the subset of it, which we're calling V. So any questions about 11 dimensions? Yes, please.
Yeah, I was wondering about if you add a cosmological constant, something goes wrong?
You want to add a negative cosmological constant, presumably, to put in an anti-de Sitter space.
So that would be cool, or positive.
Well, you break supersymmetry if you add a positive one.
Okay.
So then you're outside the realm of positive gravity theories. I think that you cannot add a negative cosmological let me think.
You can't add a cosmological constant
Yeah.
without violating supersymmetry.
I believe that's correct. You can't just put it in by hand. You would have to find some way of generating it. And
Solutions.
there may be compactifications of this. That's right. When, for instance, we compactify some of the dimensions, then we can get a negative cosmological constant in the lower dimensional space-time, which is the uncompactified set of degrees of freedom. But that's in some sense because we're trading off some positive curvature in the compact part for some negative curvature in the other part. I mean, for instance, ADS 4 cross S7 is an example of a compactification of this, where we put some flux on the S7, and then we have an ADS 4 space. So there's a four-dimensional ADS compactification of this. There are, we believe, compactifications down to 4 dimensions with a positive cosmological constant when you compactify on a G2 and do something to break supersymmetry, blah, blah, blah. But in purely in 11 dimensions, the low-energy supergravity this can't be modified without breaking supersymmetry, essentially. Okay, so that's 11. We're done with 11.
How do you count 128 for the gravity?
You have to project out. If you look at the full, so really you would say, okay, this is 11 times 32, so it's 352 dimensional or something. That's a reducible representation. So there's some kind of trace condition on the gravitino, which I think there's something like it written down in Joe's book, which you can look at, and it projects out some subset of the degrees of. I mean, it's a reducible representation, and the gravitino lives in an irreducible representation. Other questions? Yes. Yes. So in fact, there will be higher derivative terms, and it seems that, and if you have a correct quantization of this theory, those higher derivative terms will be produced by that completion. What's that? In many cases, supersymmetry constrains the higher derivative terms to take very constrained forms. I don't know of any work in which anyone proves that those higher derivative terms are uniquely determined in this theory. I know Michael Green and collaborators have done similar things in other theories, but I don't know if anybody has uniquely constrained the higher derivative terms that there should be in M theory.
Is it known that there are supersymmetrizable? Because like in 10 dimensions, there's like R to the 4th is something you can have.
Yes.
Is there something like that here where
Frankly, I've not seen people discussing that. I think that there will certainly be some higher derivative terms like R to the 4th terms just appearing from loop diagrams and various alpha, not alpha prime, but there are various corrections to this. There are membranes that do various things.
There's the lift of the Green-Schwarz term. There's a term like the Green-Schwarz term, but C3, which has a needed for anomaly cancellation.
You mean with the R wedge R?
With the R wedge R.
Yeah, that's a good example, actually. Thanks, Oliver. That's a good example of a higher derivative term. So there are some known higher derivative terms which will appear in this. But I don't think anybody has really systematically constrained those. Other questions? Okay. Now let's go to 10 dimensions. So in 10 dimensions, we have two choices. We can look at the theories with 32 supercharges, or we can look at theories with half of that number, 16, because in 10 dimensions, we have, just like in 4 dimensions, we have a gamma 11 in 10 dimensions. We're going to take the conventions as usual, 0 through 9 and 11. Gamma 11 is the product of all the other gammas. This is like a Just like gamma 5 in 4 dimensions, it projects into 2 different Weyl spinor components. And in 11 dimensions, in 10 dimensions, we have Majorana-Weyl chiral spinors, which can either be in a 16 or a 16 prime. So let's start by talking about theories with 2 supersymmetries. And these are basically the type 2A and 2B theories. And people may have seen this before, but just to kind of remind you how these theories work, there are 2 consistent supergravity theories with 32 supercharges in 10 dimensions. The first one is type 2A, which has 2 supersymmetries of opposite chirality, a 16 and a 16 prime. And this theory can be realized by just taking M theory, taking 11-dimensional supergravity, and wrapping it up on a circle. So let's just quickly review that because we want to be wrapping theories on more and more complicated things in subsequent lectures. So let's just remind ourselves how it works if we wrap a theory on a circle. So if we take 11-dimensional supergravity, we wrap it on a circle and get a 10-dimensional theory. The massless fields which remain, there are, of course, Kaluza-Klein modes coming from things with momentum around the circle. But the massless modes will consist of the various massless modes of the 11-dimensional theory, and I'll focus on the bosonic modes here, where various indices can be wrapped on the compact direction. So for instance, the graviton g mu nu, if none of the mu or nu indices take the values of the compact direction, then we just get a g mu nu. If we have g mu 11, it'll give us a vector field. This is the Kaluza-Klein story, that you compactify in 1 dimension, you get a Kaluza-Klein vector field. And G1111 just gives us a scalar field. Similarly, if we take the antisymmetric 3 form and project it down, because these are antisymmetric, at most 1 index can be an 11, and so we get a 2 form and a 3 form. So the bosonic content of 2A consists of the metric, the B field, and the dilaton, which are in the n equals 1 multiplet, and a 1 form and 3 form field, which, because of their origin in string theory, are referred to as RR fields. These are higher, in general, higher index antisymmetric fields. A mu is just a regular vector field, but C is like the 3 form field, the 3 form potential of supergravity. So that's one of the 2 10-dimensional theories with 32 supercharges. There's a second theory, which has 2 supersymmetries with the same chirality. And you can write down the supersymmetry algebra, and you get the same n equals 1 multiplet, GB and phi. And then you get, instead of the 1 form and the 3 form, you get a 0 form, a 2 form, and a 4 form, where the 4 form obeys a self-duality condition, basically saying that star dd equals dd. So that reduces to the number of degrees of freedom to 1/2 of the number of degrees of freedom that you would have if it didn't obey the self-duality condition. So just like in 11 dimensions, in 10 dimensions with 32 supersymmetries, the supergravity theories are uniquely determined by the condition of supersymmetry. So again, just the condition of supersymmetry in gravity is very constraining when you have 32 supercharges. Questions about that? Yes?
There's also massive type 2A, right? Is there any way of connecting that to another 11 dimensional?
So massive type 2A think about that for a second. Yeah, how does massive type 2A?
You can't get the massive type 2A from the normal 11-dimensional supergravity construction.
No, but it's certainly an apparently acceptable theory. I'm just trying to figure out what it, Tom, I'm sure you have something useful to say.
Just a couple of comments.
Tom doesn't like massive 2A, but yeah, go ahead.
Massive type 2A has a cosmological constant, which if you actually go into string theory is quantized in Planck units.
Yep.
And so its meaning as a low-energy effective field theory is very problematic. That's point number one. The second is I know of at least one attempt by Chris Hall to realize it as some compactification on a rather weird 3-dimensional space.
Yes.
M theory of the 11-dimensional supergravity. I'm not sure whether it's right, but there's at least one attempt.
I'm aware of that attempt. I'm not sure if it's right either. But let me go back to your first point for a second, which is a good one. So what Tom is pointing out is that it's hard to make sense of massive 2A as a sensible low-energy theory. And there are actually, it seems, a lot of limits of string theory which we don't have a clear understanding of as a massless some low-energy theory. There are theories like on five-branes and things, which it seems hard to understand in terms of the low-energy Lagrangian. So 2B is an interesting case because there's no Lagrangian, but we still believe we know what we're talking about in that theory.
I think
Yeah.
that the string coupling is weak enough. The scales allow a large effective description. I think.
Isn't that just 2A then, though? If you.
It's string scale.
Oh, I'm sorry. You're saying as an 11-dimensional theory.
It's a 10-dimensional theory. You're talking about massive 2A.
Yeah, the cosmological constant is string scale.
No, it's smaller by powers of G. Okay.
Let me take this offline.
Now, but
Yeah.
It comes up to some of the applications, some of the AES instead of rules, where you use the 10 form box.
I think we could have a really interesting conversation about this, and let's have that. But let me get through a little more material today. Massive 2A is an excellent question, how it fits into this story. I'm not going to say, I don't have anything intelligent to say about it, obviously. What I do want to talk a bit about today, which is one of the key things here, which will play into what we're talking about in later lectures, is what happens when we go down to a chiral theory of supergravity in 10 dimensions. If we have just one supersymmetry with 16 supercharges, then there are two different multiplets. There's the gravity multiplet, and there's the gauge multiplet. So gravity multiplet has just these guys plus the fermions. Yes?
Just to be picky, type 2B was chiral also.
Yes, good. And we'll mention that. So 2B is also chiral. This one has the advantage that you've got fewer supercharges, so it looks like you have more freedom in your choice of theories. Yes. Didn't mean to imply that this was the only chiral theory. Thank you, Oliver. Good. So if we have one supersymmetry, we can have not only a supergravity multiplet, but also a vector multiplet. And the Lagrangian, again, has a form something like this, where we have the field strength squared. And I'll talk a little bit more later about how something like a Chern-Simons term appears. But in the original supersymmetric Lagrangian, at lowest order in the derivative expansion, these are all the terms we have. The H field, which is the curvature of the B2 form field, has an extra term in it required by supersymmetry, which is a Chern-Simons term whose exterior derivative is trace of f wedge f. And this, I think, was shown by Berg-Schaff and others, Chaplin and somebody else, was shown is needed in both abelian and non-abelian theories for consistency of this under supersymmetry. So in principle, then, from the classical supergravity point of view, it looks like we can have any gauge group we want. We can take n equals 1 supergravity and couple it to any gauge group. So in this kind of global picture I'm trying to draw, we would have the question, does G10 have an infinite number of different discrete components corresponding to each of the different possible gauge groups? And the answer is no. And the reason is because there are quantum anomalies which constrain the set of things that we can add into the theory. And again, this is more than a 20-year-old story, but I think it's worth going through it a little bit in some detail because it's going to play a role in some of what we're going to do in later lectures, especially when we get down to 6 dimensions.
Excuse me?
Yes?
Is this the only quantum constraints?
Is this which?
Anomalies?
This has nothing to do with string theory. This is purely a condition having to do with the form of the low energy action and the content of the chiral matter, which leads to both gauge and gravitational and mixed gauge gravitational anomalies. So this is true whether or not string theory has anything to do with the world or whether or not you're looking at string theories. So what I want to first talk about is this set G, right? Forgetting about string theory, I want to talk about what is the set of theories G, which we can't rule out. And the way we're going to rule things out is by anomaly cancellation, right? Then after that, we'll ask which subset of that is realized through string theory. Okay? But yeah, this condition is independent of string theory. Okay, so let me just remind you a little bit about anomalies. So in 4 dimensions, you have the famous chiral anomaly. And The simplest thing that this leads to is a non-conservation of the chiral current J5. And you have various ways of thinking about this. You can think about it in terms of a loop diagram leading to a violation of that symmetry. Or you can think about it in terms, as Fujikawa pointed out, in terms of a lack of invariance of the measure in the path integral under that transformation, which basically means that there's no way of regulating the theory to preserve the symmetry. Mathematically, the anomaly is related to the index theorem. You can see this is coming out as the sort of thing you see in index theorems. And it has to do with the existence of chiral solutions to an equation like the Dirac equation. So this is the chiral anomaly. If we have a theory with chiral fields, then the same kind of anomaly calculation leads to a breakdown of gauge invariance. And while it's fine to have a chiral anomaly, that we have theories in nature where you see that, if you have a breakdown of gauge invariance, that really destroys your theory because you know that the theory has to have a massless photon, and the only way the masslessness of the photon is preserved is through gauge invariance. So anomalies in a local symmetry really represent a quantum inconsistency. So that's one of the things which we will try to use to rule out theories and say those are just sick. We can see from the low energy point of view, because the anomaly is really a low energy phenomenon having to do with the massless low energy content, that the theory is not viable. Okay? So in dimensions of the form 4k plus 2, which in particular include 2, 6, and 10, if you look at the nice little table in the back of Joe's book of what the transformation properties of spinors in various dimensions are, you see that in those dimensions congruent to 2 mod 4, the Weyl representations are self-conjugate. So that means that if you have a particle and you look at its antiparticle, that's got the same chirality. And that can lead to gravitational anomalies in the same way that chiral particles in a gauge theory can lead to a breakdown of gauge invariance. So in 10 dimensions, there's the potential not only for gauge anomalies, but also for gravitational anomalies and mixed anomalies. From the diagrammatic point of view, we can think of these as coming from a hexagon diagram, generating terms of the form r to the 6th, f to the 6th, and various mixed terms. And there's a nice way of thinking about the full anomaly in terms of a d plus 2 form, the anomaly polynomial, which kind of captures all the information from the hexagon diagram. And this is related to the actual anomaly through these descent formulas. So I12 is di11, and the gauge invariance of I11 is di10, where I10 is the variation of log z, which is the anomalous variation of the partition function. So there's a connection between the failure of the theory to be gauge invariance measured in the failure of the partition function to have a vanishing variation under the symmetry through this descent set of formulae to this 12-form anomaly polynomial, which captures all the useful information about the anomaly. Okay. So, in a rather dramatic bit of work, Alvarez, Gaume, and Witten, more than 20 years ago, did the calculation, pointed this out, first of all, did the calculation, and found that if you have spinors in the eight-dimensional representation and gravitinos and or anti-self dual fields, then you get these contractions of the anomaly polynomial. They look like god-awful, but that's what you get. So in any consistency, these things added up with simplicities of the particle content a lot of feedback here. Maybe battery. Okay, well, let's try to get to the end before the batteries on my amplifier die. So as Oliver kindly pointed out, in fact, the type 1 theories are not the only chiral theories. Type 2 are also chiral. So a good test, which is what Alvarez, Gomez, and Witten did, is to look at the type 2b theory and ask, is this thing really anomaly free? Yeah, get some more batteries for that. There's no gaugino. There's only the 8. So we said that in type 2b, well, it's gone now. But thank you. In type 2b, there's a 8' spinner, two 8' spinners in the gravity multiplet. I guess those are dilatinos. So we get -2 in the 8' of these guys. We have a gravitino and a self-dual tensor field. So the test of anomaly cancellation is, so if there's no gauge field, all the terms with f squared vanish because there's no gauge field, there's no gauge anomaly. If we have 2 of these guys, we can replace n here with 1, say, and multiply that by -2, just to be clear. So we have -2 times I8, where f goes to 0 and n goes to 1, plus twice this thing, plus this thing has to go to 0. And if you look at it remarkably, that works, right? This is 495. Subtract 1 from it, you get 496, and then double it, because we have 2 of each of those. We get -496 times 2 is 992. It nicely cancels that. Same thing happens in this column. Same thing happens in this column. 63 plus -63 minus 1 is -64. Double it, and it cancels the 128. Beautiful cancellation. So as Alvarez, Gomez, and Witten pointed out, this theory is a sensible low-energy theory, and somewhat miraculously, it is the one theory which we get out of string theory, that it has 32 supercharges. So that's cool. For n equals 1, on the other hand, it looks like the story is much more murky, because for n equals 1, we don't have this self-dual multiplet, or an anti-self-dual multiplet, so we have to somehow get a bunch of these and a bunch of these to cancel. But it just takes a little bit of looking to convince yourself that if you set these guys to cancel on the first column, you'll have to set n as 495, and that certainly won't cancel in any of the remaining columns. There's no way to get those two terms to cancel by just manipulating this and this, by the I8 and the I56. So it looks like, from the point of view of regular anomaly cancellation, you can't get rid of the anomalies in this theory. Questions?
Where does n come from again?
So n is the number of spinner fields. If you have a non-abelian gauge group, you'll get some from the non-abelian gauge group, and then you'll get some if you have a dilatino. Other questions? Those are the dimensions of those representations. So the spinner is an 8-dimensional representation. The gravitino is 56, and this anti-self-dual thing, I think, is 70. If you take 8 times 7 times 6 times 5 and divide it by 6 times 4 and divide by 2, you should get 70.
Maybe I didn't understand because the question you addressed in page 8.
Question I addressed in page 8. What's the question? This question, does it contain infinitely many components? Well, the point is that at this stage of the game, all we know is that you can have any number of vector fields you want from the point of view of classical supergravity. So in fact, where I'm headed right now is precisely addressing that question. In other words, naively, classically, it looks like you can add all the gauge fields you want, and there's no problem. You just couple them into the supergravity theory. The question is, are there constraints? And the constraint that we're going to talk about is anomaly cancellation. And the place we just got to is that it does not look like anomaly cancellation will allow any such theory.
So you say there's a fixed number of the gauge fields by anomaly cancellation.
Well, the question we're asking is, can you say anything about the set of gauge groups that you can get by anomaly cancellation? And so far, from what we've said, it looks like no gauge groups are allowed because you can't possibly cancel the anomaly. So far, right? But Green and Schwartz came to the rescue with their marvelous discovery of an anomaly cancellation mechanism. Basically, there was this problem that the supergravity plus Yang-Mills has hexagon diagrams which can't be canceled. And basically, by carefully treating the couplings of the B field, and by introducing new B field couplings at higher order, they were able to get tree-level terms which cancel the anomalies. So let me just walk through that in a little bit of detail. So the idea is that the action is expanded. Remember I commented that we had, because of supersymmetry, we were forced to have a term in the action which looked like a dB squared, an h squared, but we had to add, by supersymmetry, a Chern-Simons term for the gauge field. Well, in order to get their mechanism to work, they add in further something proportional to trace, whose curvature is proportional to trace r squared, a Chern-Simons type term for the spin connection. And at first, you just put these in with some arbitrary coefficients, and then these will be fixed by the anomaly cancellation condition. So imagine that these things, actually the coefficient here is of course fixed by supersymmetry, but you can imagine putting these guys into an arbitrary combination and calling it y4, where y4 is a 4 form. Then you put in a Chern-Simons term, B wedge some 8 form x, which is a function of f and r. Now, as soon as you do this, the variation dB is going to have a term coming from the variation of omega Lorentz, omega Yang-Mills, and a term from the variation of omega Lorentz in order to preserve the gauge invariance of the theory. And what that means is that this term that you've added is not a gauge invariant term. So basically, their suggestion is add some tree-level interactions which are not gauge invariant, which basically involve the coupling of the B field to various different form fields. And if the anomaly polynomial can be brought into a product form, which factorizes into a 4 form times an 8 form, then that can be canceled by tree diagrams of this form. Because basically this term right here is essentially like BF4, BY4, and then you get a BX8. And so there's a tree diagram where you get this factorization to come in looking like this.
Is that a unique way to cancel the anomaly?
As far as anyone knows, that is the unique way to cancel the anomaly. And it's very hard to imagine how else you could do it. People spent a long time trying to cancel the anomaly. As I understand it, I wasn't around then, wasn't engaged then. As I understand it, people spent a long time trying to cancel the anomalies without this mechanism. And Green and Schwartz discovered this mechanism, and it was kind of, if I understand it, was kind of miraculous because people thought you couldn't do it in any way. And this indicates that yes, with this extra tree level thing, which it turns out is the way it's done in string theory, this anomaly is canceled. Yes, question? Well, the term, an anomaly is a breakdown of gauge invariance, right? So if there's an anomaly and you add a term which violates gauge invariance, you may be okay. And in fact, what they showed was that the violation of gauge invariance from the anomaly is precisely canceled by the violation of gauge invariance from this extra term they added, right? So it all works out. I'll be a little more explicit about that.
Does that mean classically it looks non-gauge invariant?
Classically, it looks non-gauge invariant. You have to add the one loop term to restore the gauge invariance of the theory. That's absolutely right. This is a higher derivative term, so it's all a little funny. But no, it's not a little funny. It all makes complete sense. But you have to be careful. That's all I'm saying. Yes?
Can this term derive from string diagrams?
Yes. In fact, if I understand correctly, that was perhaps part of what gave Green and Schwartz their intuition for how this might work. But you certainly can derive this from string. In their paper, they include the string derivation of this and show that this is the way it actually works.
But the anomaly cancellation should impose a constraint on this collection.
Absolutely, it does. That's correct. And that correct coefficient is reproduced in string theory. Yeah, good. Other questions? Okay, so let's just see how that actually works. So basically, the anomaly polynomial, if you write it out, it's got a term proportional to trace r to the 6th with an n minus 496 out front. And then it's got a term proportional to trace of f to the 6th. And then it's got all kinds of terms with f to the 4th f squared, various cross terms and things like that. And what we want is for that thing to be expressible as a product of, or what Green and Schwartz wanted, was for that to be expressible as a product of a 4 form and an 8 form so that this mechanism comes into play. So for that to happen, basically two things have to happen. The r to the 6th term obviously can't be part of this factorization, so it has to go away. Therefore, the number of gauge fields must be 496. This thing can only cancel if the f to the 6th term goes away. And if you algebraically manipulate this whole thing, you can get it into a factorized form precisely when trace f to the 6th can be re-expressed in terms of lower order terms in traces of powers of the gauge group, field strength. Now, this identity is satisfied for precisely 4 groups of rank 496. Those 4 groups are SO32, E8 cross E8, U1 to the 496, E8 to the U1 cross U1 to the 248, and that's it. So all other theories are ruled out by anomaly cancellation. These 4 gauge groups satisfy this condition, and between those and 2A and 2B, it seems now that we have 6 candidates for a UV-consistent supergravity in 10 dimensions. Okay, so that's our G. Any questions about that? We've successfully determined a set G for 10-dimensional n equals 1 supergravity, and it has 6 elements in it so far. Okay, yes, question?
Maybe I'm missing out something, but you add parameters in your problem, and then you fix them, right? So such that you keep the gauge invariance. Couldn't you play the same game with some other theories that are anomalous? Add some terms classically gauge invariant, but with an arbitrary.
No, you would have to do it in a very careful way, because you would have to add a term whose variation was precisely correct to cancel the gauge anomaly. And if you could do that, you would have written down a Lagrangian which was non-anomalous. So perhaps there are certainly classes of theories where you can do it, and we'll talk about some other ones as we go through these lectures. But it's a non-trivial thing to find a theory with an anomaly and then find a way of fixing it, which isn't just writing down an obviously non-anomalous theory.
Is this adding terms or fixing gauge group?
Terms are being added to the action at higher derivative order with specified, in terms of, forgetting string theory, in terms of the low energy theory, we are adding terms to the Lagrangian, which appear to be non-gauge invariant, but which in the quantum theory restore gauge invariance.
Only at one loop? Or
Good. So it is certainly possible to imagine that this might work, might appear to work, but then might break down at some higher loop order, that somehow this gauge invariance is going to break somewhere higher. For those theories that can be realized in string theory, if string theory is correct, then that will be fixed at all orders. So all we've done, really, I want to focus on the question of ruling things out rather than ruling things in, because it's very hard to rule something in. It's very hard to say that something is a consistent theory of quantum gravity unless you know how to realize it in string theory, and even then some people will argue with you. But the thing we can do is we can rule things out. If it's anomalous already with this stuff and we can't fix it up, then we're done. Then we can say, no, it's bad, we'll throw it out and we won't think about it anymore. So you certainly want to think about the things that you can't realize. I mean, in some sense, much of the research program I've been kind of trying to follow in the last year or two is basically to consider this set G and the set V in various contexts and try to find examples here and try to ask, what's up with that theory? Can we either rule it out or can we find a string vacuum? Because that's an avenue towards progress, right? And what I'm kind of trying to emphasize throughout these lectures is, in every dimension, starting from 10 going down, there are questions like this. There are theories that we don't know how to realize in string theory and we can't rule out. And maybe by studying those, we'll learn more about string theory or about low energy consistency conditions, which may be relevant all the way down to 4 dimensions. So, as I said, there's questions like this in every dimension except 11, basically. There we go. Okay, let's see. 5 minutes. Okay, so we've got G, this big set for 10 dimensions. So the next thing we want to talk about is, what's V? So let me just spend the last 5 minutes or so talking a little bit, just in sort of general terms, about string theory and branes and things like that. So how do we get real UV completions of these theories? In other words, we're changing gears from ruling stuff out to ruling stuff in, finding this set V. How do we realize quantum theories of gravity? The way that we know how to realize quantum theories of gravity, in general, consists of considering extended objects which couple to p-form fields. So just like a point-like particle couples to a mu, a p-brane couples to a p+1 form. It's just an integral over the world volume of the gauge field of the antisymmetric tensor times the wedges of the dx's. These things couple in the same way. And we have lots of examples of this already in the things we've just talked about. In 11 dimensions, we have this 3-form field, and there are 2 branes that couple to that. There's an M theory, a 2-brane in the theory, which carries charge under this field, under the 3-form field. In 10 dimensions, if we have 2 supersymmetries, the only antisymmetric form field we have is b mu nu, and in both of those cases we have a fundamental string, something which is charged under b mu nu and which is an extended object of that form. In 2a and 2b, we have a richer set of things. We have d-branes. So in 2a, where we've got a gauge field and a 3-form field, we have 0 branes and 2 branes and 4 branes and 6 branes, which are the magnetic duals and things like that. And in 2b, we have a D string, D3 branes, etc. Now, the great insight that Joe had a while ago is that we can think of these things in terms of string theory. But more generally, I would say the lesson we've learned over the last 20-some-odd years is that if you take any of those branes that couples to some p-forward field, and you work as hard as you can to quantize it, you will get some information about a theory of quantum gravity. Sometimes it's hard, and sometimes you have to go into some exotic limit to make sense of that. But pretty much every brane that we know of, and especially the lower dimensional ones, if you can get some sense out of a quantum theory of that brane, you're suddenly learning something about quantum gravity. So, one example of this is in 11 dimensions. You can take the M2 brane, and as Tom mentioned a little while ago, you can take a relativistic theory, go into the light cone, and make sense of it. This was done by Goldstone, Hoppe, Nicolai quite some years ago for the for the 2 brane, when people were trying to look at the 2 brane as a fundamental object, and they successfully wrote down a matrix quantum mechanics associated with that theory, and it appeared to have some problems. And then years later, Tom and collaborators Fischler, Schenker, and Susskind came along and said, look, we can get matrix quantum mechanics from D0 branes. And they got a theory which turned out to be the same sort of theory that these guys had gotten by quantizing the M2 brane, and it's a quantization of M theory. So if you quantize either the M2 brane or D0 branes, you get a version of a quantization of M theory. It's a little restricted because it's in a light cone gauge, and therefore it's hard to do some of the things we want to do, but it's a beautiful quantum theory of gravity, and it's very simple because it's just quantum mechanics. In 10D supergravity, we can take DP branes, and Joe drew us a beautiful picture in his lecture of how really, in fact, he had this little picture over here, of how quantizing the DP brane in a certain limit gives us a Yang-Mills theory, right? And you quantize, I'm just calling back to what he had on the board, not what I've got here. And if you quantize the black brane, which is the gravity solution, you get the same theory. You get supergravity in an ADS5 cross S5 background. So quantizing the D branes give us ADS CFT as another description of quantum gravity. And of course, the oldest version of this is quantizing strings, which give us perturbative string theory. This is best understood in Ramon backgrounds with G, B, and Phi. It's a little tricky it's best understood in NSNS backgrounds. Ramon backgrounds are tricky. D branes in this language are loci where the endpoints of open strings live. And one of the beautiful discoveries in this context was that the strings stretching between branes lead to a non-abelian gauge group enhancement so that n branes on top of each other, as again Joe was describing, give you an SUN gauge theory. So this leads us to a quantization of all these different string theories. We can get 2A and 2B, the two n equals 2 supersymmetric theories in 10 dimensions by quantizing the 2A and 2B string. We can get E8 cross E8 and SO32 cross Z2, which is equivalent to the type 1, also by quantizing strings. So this gives us now a global picture of what we know about the 10D space of supersymmetric gravity theories. We've got a space G with 6 theories in it, which we can't rule out. 4 of these are realized in string theory. So the apparent swampland has 2 theories in it. So the remaining challenge is in 10 dimensions. There's going to be a challenge in each dimension. And the challenge in 10 dimensions is to either find a string realization or rule out these two theories. So I've been puzzling about this for a while with Oliver and Alan Adams, and I can't help but mention that last week Oliver came out to Boston, and we think that he and Alan Adams and I may have proven that these two extra theories are inconsistent, but there's a good chance this will fall apart in the next week or so, so I'll tell you more about it later. The reason I mention this is not because I think we're necessarily right, but I hope we are, but to point out that even in this ancient story by now, 25 years old, there's an interesting open question, which is, what is the fate of these two theories? Are they realized in string theory? Are they sick? So there's interesting work to be done already in the most well-understood of these contexts. And the set of open problems will become just bigger and bigger as we go down in dimension. And for the rest of this, I should mention I will focus primarily on the non-abelian part of the gauge group because, as we've seen here, theories with abelian parts are a little more subtle. Worked out pretty well for the time, so I'll stop there. Take any last questions? Questions? Yes, please.
I get the impression that you're saying you identify the entire but like.
Sorry, say that again?
I get the impression that you're saying that you identify the whole G or even the identity.
Assuming supersymmetry.
Right, but for each of, like, say, like type 2B, like, are there many ways to perform the theory?
There are moduli. There are scalar fields whose values could start around different values, which would give you different backgrounds. Not in any way which I'm familiar with, which is consistent with supersymmetry, which is not represented as a modulus. Do you have an example in mind? I'm not sure what you mean. In lower dimensions, there are more ways of deforming things, but there's also more moduli. That's part of the moduli problem. In lower dimensions, there are things like fluxes you can turn on, but those have to do with structure and the compactification from higher dimensions. So that's partly why we're starting in higher dimensions, because in higher dimensions, there's not a heck of a lot you can do. You're very constrained. And so what we want to do is move down in dimensions and see how as you move down in dimensions, you get more and more tools, more and more widgets that you can throw into the construction, which give you those degrees of freedom. So there are lots of those degrees of freedom, and more of them as you go down in dimension. But in 10 and 11 dimensions, you are very constrained, just by supersymmetry and quantum consistency. Maybe another question? If there, yes, please.
So how does the story change if you allow for orbitals in some n dimensions?
So the theories I'm talking about here are 10 and 11 dimensions in flat space-time. When we compactify, you might talk about compactifying on an orbifold, and that would be one of the widgets that you can add in compactifying to lower dimensions.
You may not compact me.
You mean an orbifold like, so type 1, for instance, is an orbifold. And why don't we save that for actually the 1 or 2 lectures from now when I will talk about type 1, which is an orbifold of type 2b. There's a way of thinking of an orbifold of type 2b. I do not know of other...
like take care of all possible combinations? I mean, I know the type 1 example.
Yeah, I don't know of any other orbifold examples in 10 dimensions. If they gave rise to low-energy supersymmetric theories of gravity, by the arguments that we've just given, they would have to give you one of these 6 theories. Right? I mean, because the arguments here really had nothing to do with string theory. They were what theories are allowed by the multiplets of supersymmetry and by consistency conditions like anomaly cancellation. I haven't put anything more than that into the definition of this set G. That's partly why I think it's worthwhile to focus on these 2 separate sets. The set G is the set of information that we have which is independent of string theory. You can start talking about orbifolds or all kinds of exotic things, but if you can make some hard and fast rules about what's not allowed by the low energy supergravity and quantum consistency conditions, then you have a lot of knowledge about what you're going to be allowed to do. That's kind of going to be the theme of these lectures, is playing off these 2 things against each other. Are there a last question? Yeah.
Can you comment what goes wrong?
I'll tell you what, if by the end of the week it hasn't fallen apart, maybe I'll say something in my last lecture. How's that? Other questions? Okay. I guess next lecture is at 2, is that right? Yeah. Yeah, Joe, Oliver and I are hoping to buttonhole you sometime this afternoon and ask you.
Can't you use if you have